So let's figure out what transition systems are all about. We shall introduce transition systems by means of an example based on the game of Towers of Hanoi. The game of Towers of Hanoi has a number of rods and a number of discs, 3 in this example. The rods are called A, B, and C. There can be 0 or more discs on either rod, but there is a rule that if there is more than one disc on a rod, they have to be in decreasing size from the bottom to the top. So in the example on the right, there are no discs on the rod C. The smallest disc around is on the rod B, and on the rod A we have the medium and the large size discs. We shall need some notation to express the placement of discs on rods. And for the example on the right, we shall be writing little b, medium-sized A, and large A to indicate that the smallest disk is on rod B, the medium-sized disk is on rod A, and the largest disk is also on rod A. The fact that the largest disk is below the medium disk will be automatic because we will always observe the rules of the game. A transition system is then a directed graph. The nodes are the states, that is, the placement of disks on rods. The edges indicate the moves we can make in the game, following the rules. It might be worthwhile to take a small break and identify the placement of the state, little b, medium A, large A, and to look at some of the edges and realize that they do in fact correspond to legal moves in the game. To give the formal definition of what a transition system is about, we shall be based on a simpler example. The transition system we are having here is having just 4 states labeled A, E, G, and H. And there are 5 edges indicating the ways we can move between the states. And there is a dotted edge indicating the initial state of the transition system. In transition system, every state is labeled. And here we have a labeling function that tells us that the label of A contains only the label V, which is supposed to stand for vowel. Similarly, the label for E only contains V, standing for vowel. The label for G only contains C, standing for consonant, and the label for H also only contains C, standing for consonant. In general, a transition system consists of a non-empty set of states, which we call S. In the example on the left, it was A, E, G, and H. And a non-empty set of initial states. In the example on the left, there was just one, namely A. And there will be a transition relation, indicating how to move from one state to another. And we usually use infix notation for this transition relation. And finally, there will be a set of atomic propositions, in our case V and C, and a labeling function that for each state tells us 0 or more of these atomic propositions that hold at that particular state. Sometimes it is helpful to use the atomic propositions and the states in the same way, so that the label of a state is just the state name itself. In the case of Towers of Hanoi, we will have the states as indicated here. The initial state is the one where all the disks are placed on the rod A. The atomic proposition is the same as the states, and the labeling function just assigns the state the single atomic proposition being that state. We need some concepts for how to move around within a transition system, and that is the notion of a path. We start at some state, follow an edge, get to another state, follow an edge, get to another state, and so on and so forth. However, we have to continue as long as we can, which means that a path will be either infinitely long or will end in a state from which there are no outgoing edges. Such a state is said to be stuck. If we need to talk about shorter sequences of states that are related by the edges, we can use the term path fragment. The symbol we use for a state might be a little bit unfamiliar. It is the Greek letter sigma, but written in sort of handwritten notation, and we call it var sigma. Some notation to capture these ideas is the following. Path of var sigma 0 will denote all the paths starting in var sigma 0. Reach 1 of S0 will be the set of states reachable in just one step from a state in S0, whereas reach of S0 would be the set of states reachable from some state in S0 taking 0 or more steps. Now it is time to pause and figure out what these concepts mean for the Towers of Hanoi example. Are there stuck states? Are there any infinite paths? Are there any paths that are only finite? Try to trace the shortest path fragment from the state where all of the disks are on the rod A to the state where all of the disks are on rod C. Which states are reachable from the initial state? Which states are not reachable from the initial state? What can be reached in one step from the state ABC? What can be reached in any number of steps from the state ABC? Once you've done this, you should read the section in the book doing the try it outs on the way.